They were definitely an interesting set of questions, and thank you for trying them, but they were tough. We found them difficult, and I think that's going to be the nature of things just now. We can do everything that we can, kind of trying to teach it online, looking at videos, things like that, but it's never going to be the same. So don't worry if you're not feeling confident with this just now. It is definitely something we're going to look at when we get back into school. But what I thought would be really useful is if I go through some of these questions, what I'll do is I'll give you exactly the same set of questions to look at next week, but we'll do it as a kind of shadow paper type thing where we change some of the numbers. So you've got this video to walk you through it. You've got a set of model answers that I'll put onto the shared Google Classroom as well. And you can use those things to kind of see, well, what's the structure here? How does it work? And actually, as we get into it, it will make a lot more sense. The work we're doing just now is actually the things we'll be teaching at the end of year 13. And the reason I picked it is conceptually, it's not really difficult stuff about fields that we'll look at later on. I'm not really going to touch on any of that while we're not in school. But what is difficult about this is that part where you've got lots of different equations, lots of different ways of putting them together, and you've got to decide, well, how's the best way of doing it? So I suppose in a lot of ways we're practicing skills for the end of year 13 right now, and I think it's testament to the four of you about how well you have been doing across this year that I feel you're kind of ready to start tackling. That's really well done for that, right? We'll look at some of these questions. What's really nice is the way people have tackled different bits. So for example, in part 8 here, you've been told the half-life is 5,740 years. That's a number that keeps on coming up. Carbon-14 is kind of a standard example that we use. You're not expected to know that number, but the fact that it's there kind of can fill you with confidence. But working half-life into decay constant, well, that's a really easy thing to do. So we know that the decay constant is equal to log 2 over the half-life. Now, we've got two options here. Half-life and decay constant should always be written in seconds and per second. They've given it to us in years, but they've also asked for the decay constant in per year. So what I could do is I could take this number, I could turn it into something in seconds. So I've got a conversion factor for that, work out my decay constant in per seconds, and then convert that back into per years. But what I'd end up doing is timesing and dividing by the same number. And the fact that this question is only worth 1 mark, that can be a lot of hard work. So actually, I'm just going to leave it exactly as it is, because we think unit-wise, if I've got 5,740 years here, well, my unit for my decay constant is going to be per year, purely for what's going on there. And if we put that through, we'll get an answer out of 1.2 times 10 to the minus 4 per year. Now, for the second part of this question, a piece of wood is taken from an axe handle from an archaeological site, and it's got 0.375 times as many carbon-14 atoms as an equal mass of living wood. Now, quite a strange way of phrasing things. This is actually saying there is less carbon-14 in the sample that we found today than we'd expect to find in living wood, and that's exactly what happens. In a living sample, there's a certain amount of carbon-14, and it's continually replenished by everything that's respiring. When it dies, it stops respiring, so the amount of carbon-14 is fixed, and because it's radioactive, that kind of decays away over time. So we've got less of it. So what we're expected to use here is this whole, the number of radioactive nuclei I have just now is n0 e to the minus lambda t. Decay constant they're giving us, the time we're trying to work out. And in the question, they've told us our ratio, the number now compared to the number at the start, is at 0.375. So that's where this is tricky, this question. It's about how they've written it rather than the maths we're doing. So let's put those numbers in. 0.375 is equal to e to the minus lambda t. Log 0.375 minus lambda t. So t will be equal to 1 over lambda, which is the 1.2 times 10 to the minus 4 that we've worked it up here. Log 0.375, and there is a minus sign that I don't want to forget. If I stick all of that into my calculator, I'll get 8,100 years. 8,100, 8,200, depending on what numbers you've used in terms of your rounding. So this part is the tricky bit in terms of reading the question. After that, we're just putting numbers in to work it out. So part B is a bit of an understanding thing here, right? So what we're going to remember is that our half-life for this sample is 5,740 years. And that's what's going to give us our answers here, right? So suggest why this method of carbon dating is likely to be unreliable, if the sample is less than 200 years old. Well, what we're basically talking about here is, well, if it's 200 years old and this is the half-life, barely gone through any of a half-life. So there's only going to be a very small change in activity, which would be really hard to measure. If it hadn't gone through at least a couple of thousand years, we're not going to be able to tell the difference between something that is 0 or 200. So that's the kind of thing we're looking at there. If it's more than 60,000 years old, well, my half-life is roughly 6,000 years. So this is looking at roughly 10 half-lives. If it's gone through 10 half-lives, well, there's going to be very, very little of the radioactive carbon-14 left. So here, there'll be very little activity to detect. Helps if I can spell. So question 2, we're emitting alpha particles. Graph shows the rate of decay of the activity, megabecquerels, so that mega might be important later on, and how it changes with time. I mean, anytime you see a graph like this, you can kind of see some kind of radioactive decay constant half-life type question that we can use, right? So from this, determine the half-life of the radionuclide. Well, this is our kind of standard, can we draw it from a graph? So what we have to do is kind of pick a decent place where the lines are crossing really, really obviously. Well, looking at it up here, that looks like quite a nice place where it's crossing over. I don't know where it's going to, where half it's going to be, that's going to be the same, but that's going to be 0.24. Appreciate it's 2 steps up. If we look at the scale, 0.24 megabecquerels. So I'm looking at 0.12. That's half. The time they're going across is going to be 50. So it's taken me 50 seconds to go from 0.24 to 0.12. So that's my half-life. So now it would like us to work out the decay constant. We've got a pattern here. It's the same kind of idea of my decay constant lambda log 2 over my half-life, 50 seconds. If I put that into my calculator per second. The initial number of undecayed nuclei present at time t equals 0. So n is equal to n0, e to minus lambda t. But I'm not trying to work out n here, I'm trying to work out n0. So this is one option. If I had the number of particles at a particular point in time, I could work out the number at the start. But what I don't have for this is the number of particles at a later point in time. So let's think about the other equations that I've got. I also know that my activity is equal to lambda n. Now I've got a graph of activity, so long as I pick my activity at t equals 0, and if I jump back up to my graph, my activity at the start at t equals 0 was 0.24 megabecquerels times 10 to the 6, because it's mega. That would be equal to lambda n. So n is going to be 0.24 times 10 to the 6 becquerels divided by my value of lambda that I've worked out, 0.014. And if we put that into a calculator, 1.7 times by 10 to the 7. So my first thought here was to try and use this equation, because that's a kind of standard way of doing this kind of thing, but it wasn't necessarily the right choice. I had to look at it and kind of went, well, I don't actually know everything I need to, so what other equations do I do? No, I found something which was a bit more useful. For part B then, each decay releases that many joules of energy. Fair enough. From the time interval between t equals 30 and t equals 50, calculate the number of nuclei which is decayed. Now, there are two options here, right? I can sit there and go, right, well, actually, using my n is equal to n not e to the minus lambda t, I could work out what n is at 30, what n is at 80, and see what the difference is. But actually, there was a little trick here. 30 to 50 is going to be 50 seconds. And we know 50 seconds is our half-life. So if I can work out the number of radioactive nuclei at 30, I know 80, there's going to be half left, so half of them will have decayed. So let's try putting those numbers in and see what works. The number of nuclei at 30 seconds will be n0 and that's what I've worked out here. E to the minus lambda 30. So that will be 1.7 times by 10 to the 7, my original value. E to the minus, well, I've worked out lambda, 0.014, 30. And if we put those values in, we're going to get 1.12 times 10 to the 7. So that's how many there are at 30. If I want to work out how many there are at 80, well, there would be half that number. So the number of decayed would be 1.12 times 10 to the 7 divided by 2, because we've gone through one complete half-life, 0.56 times by 10 to the 7. Calculate the energy released. Well, they've told me that for every decay, that's the amount of energy that's given out. So I've had 0.56 times 10 to the 7 decays. Each decay gives me that many joules of energy. So 5.6 times by 10 to the minus 6. Now, question 3 is quite an interesting question. Actually, this is a question when it was set as an actual A-level question, really threw a lot of people because it's not the standard kind of radioactive decay type thing. Now, a lot of time these questions are really, really lovely because actually anything you can do on them is worth marks. So this isn't radioactive decay, it's the model that kind of shows you how radioactive decay works. So what we've got is a tube full of water flowing out of the tap, and this water is actually representing our radioactive nuclei. And what's going to happen is these are then undecayed, and as they flow through the tap, that'll be when they're decayed. Now, what it says in the kind of blurb down this way is, well, how quickly this water flows through depends on the pressure of this water. If there's more pressure on it, it'll flow more quickly. And that pressure depends on the height. So the deeper the water, the quicker it will flow through. So the depth of the water is kind of equivalent to our number of nuclei. The more nuclei there are, the more radioactive decays we get. The bigger the depth of the water, the quicker the water flows. This tap, well, that is linking to our decay constant, our probability of decay. If the tap's open, it's really easy for the water to flow through, so there's a really high probability to decay, a high decay constant. If I close the tap, it's harder for the water to flow through, so there's less chance of decay, so a smaller value of lambda. The tap is open and the depth is measured at regular intervals and it's plotted. Well, it's exactly the same kind of graph we've looked at before. Nice exponential style decay. And we'll have a look at the actual questions in a second, but with things like this, we're thinking about half-life straight away. So I'm probably not even going to bother reading the question straight away. What it's asking me to do, I know at some point it's going to say, what's the half-life, or we would expect to use that. So I started off at 16, my half value would be 8. So going across here, that is going to be, 19 seconds. So 19 seconds is my half-life. So let's see if that bit of information comes in handy. Determine the predicted depth of water when the time is 57 seconds. Well, let's go back to my graph there. There is not 57 seconds on here at all, right? And more than one student has sat there and kind of went, oh God, how am I going to do this? How am I going to make it work? And so they've kind of started just extending the line out and sort of saying, well, I can get to like 30 on it if I go down here. So then they're getting like extra bits of paper and they're trying to trace it on further and further and further and kind of guess to where they're going to go through. And that's not the plan. That is not what they're expecting you to do. But let's look at these two numbers. The half-life is 19 seconds and it wants to know it's 57 seconds later. Well, I can grab a calculator and go, well, hold on, 57 seconds, that's 3 half-lives. So what we'd have is, at the start, we had 16 centimetres of water. After 1 half-life, it would be down to 8. After 2, it's down to 4. And after 3, 2 centimetres. So my depth there is going to be 2 centimetres. It felt like a random number. It felt like I couldn't get it from the graph because by kind of extrapolating, drawing more of the graph, you can't do that. But actually, because we sat down and went, what is the half-life? Because I know it's going to be useful, we had a really good way of answering the question. How could we represent same nucleotide with a greater number of nuclei. Well, we've already said more depth. In this model, if there's more water, deeper water, that represents more nuclei and the rate of decay will be increased. Suggest how the apparatus can be changed to represent a radioactive nuclide with a smaller decay constant. Smaller decay constant means it's less likely to decay. If it's less likely to decay, it would be a smaller flow rate, so we could close the tap. If the tap's shut, can't flow as quickly, smaller decay constant, that's our kind of equivalency here. The age of the moon is estimated from rock samples containing rubidium and strontium. And what happens is our rubidium decays into strontium, and there's our decay constant. Calculate the half-life in years. It's the same story again. Okay, now this time we're working out the half-life rather than the decay constant, but we're using the same equation, just rearranged. And actually, we can use our same trick. We should probably put that in seconds. We should do a half-life in seconds. But the fact that both of those are in years, we don't need to worry about it. We can just leave everything nice and simple. If one was in years and one was in seconds, then we might need to start doing conversion. But let's just get these numbers straight in there. 1.42 times 10 to the minus 11. So my half-life is going to be 4.9 times by 10 to the 10 years. Sample of moon rock contains that many micrograms, no, not micrograms, sorry, milligrams of rubidium. Calculate the mass in grams. So straight away, I've got a kind of difference here, so I need to be clever with that, right? Contained when it was first formed 4.47 times 10 to the 9 years ago. So well, we've written a lot that n is equal to n naught e to the minus lambda t. Well, we're not dealing with number of the nuclei, we're dealing with mass here, but it's the same side of the story that the mass is the mass at the start, e to the minus lambda t. Now, they've given me this, and they've given me this. We're trying to work out that. So let's just rearrange and make that the subject. M naught is equal to m e to the lambda t. The mass at the start was 1.23 times by 10 to the minus 3 grams. E to the value of lambda, they've already told me, 1.42 times by 10 to the minus 11. I'm being really careful not to write a minus sign there because we've kind of taken it across, we've gotten rid of that, but old habit dies hard, so it's very likely to put that there. And then the time they gave us was 4.47 times 10 to the 9 years. Now again, I've got a time in years, a decay constant in per year, so that's absolutely fine. If it was a different mix of units, then we would have a problem. If we put that into our calculator, 1.31 times by 10 to the minus 3 grams. So we started off with 1.23 micrograms. Sorry, we now got 1.23 micrograms, and we started with 1.31. So a really small change, but something that we're capable to measure, so let's actually estimate the age of the moon. Very last part then, calculate the activity of the sample of mass, 1.23 micrograms, and give an appropriate unit for your answer. Well, the activity, I know it's measured in becquerel, so we talked about getting easy marks. If I'm sitting here, I don't know what I'm doing, I'm taking to write that mark. That's a nice simple thing that we can do before we do anything else. Activity, lambda n. Got the decay constant, but I don't have n. What I've got is a mass. So what I need to know is how to turn a mass, or rather a number of, mass into a number of nuclei. So this is, I suppose, in essence, a bit of chemistry, isn't it? I can sit there and go, well, 1 mole of rubidium 87 weighs 87 grams. But I don't have 87 grams, do I? So if I've got 1.23 milligrams of rubidium 87, that's going to be 1.23 times by 10 to the minus 3 is my mass there. Oh, I'm having a moment. I might just pause there and do that again. So if I've got 1.23 milligrams of this, it's going to be 1.23 times by 10 to the minus 3 over 87. So that's how many moles I've got. If I want to convert that into my number of nuclei, my number of nuclei would be my number of moles times by Avogadro's number. So now what I've got, and I can actually get that 8.5 times by 10 to the 18 nuclei. Well, now I've got my number of nuclei. So to work out my activity, I can use my number of nuclei and my decay constant. All the way through this question, we'll be going, well, the decay constant is in per year, and that's one, because everything else is in per year. Well, my unit, becquerels, is actually per second. So this is where I need to actually start putting my decay constant into seconds. So my decay constant, which they have given me earlier, was 1.42 times by 10 to the minus 11. Well, that's in per year. So if I want to make it into per second, 365 days in a year, 24 hours in a day, 60 minutes an hour, 60 seconds in a minute, times by my value of n, 8.5 times by 10 to the 18. That's what we've worked out. And if we put all of those values in, we should come out with, he says, 3.8 becquerels. I'll put a copy of the work solutions there that I've written up onto the Google Classroom, and I'll put a copy of this video up there as well. Have a little look through. Have a little look through my solutions, have a little look through the mark scheme, and have a little think about, well, how does that work? What's going on there, right? As I said, next week I'll give you exactly the same set of questions, but all we'll do is do little things of, it won't be 1.23 milligrams, it might be 1.6 milligrams. So your job then is to go, right, how to replace it? What are the key most important things? And we're starting to build up this kind of model solution of, this is how I tackle this style of question. And as we get more and more confident, all you'll be doing is go, all right, this new question I'm seeing is just like this old question, except here's a little change, here's a little thing we can do. And that's where we build up confidence. So well done for trying these things, right? The things that are really difficult to get better. So the fact you're trying is really, really important. And the fact that people were naming bits of this, finding bits they could do, wonderful, right? Watch it a few times. We'll try again next week and we'll get it nailed before you have to sit these things at the end of year 13. So well done, everybody. Thank you for your hard work. We'll keep going next week.